We're very happy to have Spencere Cattalani from Stony Brook, who's going to tell us the Ahlfors currents and symplectic non-hyperbolicity.
Thank you very much. Thank you for letting me become a speaker. It's a joy to be able to talk about this. First, let me provide a little motivation, just to motivate the theorem. It's by Gromov and Taubes. The symplectic structure on CP2 is unique, given its volume form or something like that. The argument uses sweep outs by rational curves, and this argument works to classify symplectic structures on rational and ruled symplectic manifolds, where you have lots of rational curves. And the simplest manifold for which it stops working is the 4 torus, which is somehow also like the simplest symplectic manifold. So we don't really know much about symplectic structures on the 4 torus. But we do have this theorem, which gives us hope, by Bangert in '98. There's a non-constant holomorphic map into any dimensional torus for any J tamed by the standard form. So in light of this theorem, Gromov proposed that studying maps of this kind could help us classify symplectic structures on the 4 torus. But that seems difficult. But let me say this theorem is amazing. This is why I did this work. Just amazed by this theorem. So first of all, you might think this is trivial because there are always disks, right? I mean, this is a contractible object. Maybe it's trivial, but it's not, because the complex structure on the disk and the plane are different. And in fact, you can't have maps of this kind into Darboux charts. So it has to see some kind of global information. Also, the typical complex structure on a torus has no closed curves. I mean, it doesn't have any spheres because it's aspherical. But also, if you just look at a typical complex structure, the lattice where you expect holomorphic subvarieties to live is empty. And then if you try to prove this in the way that you prove things like this using a continuity method, you see it complicates significantly. So for instance, if you just have, by analogy with GD6 on a torus or something, if you take this and you perturb it just a little, then it sweeps out the whole manifold. So that's what happens in complex geometry when you go from a projective torus to a non-projective torus. It's to even study how a torus perturbs as a complex line, it sweeps out the whole manifold. So you need some kind of global information about the manifold to be able to do anything. It's like the standard techniques don't really tell you about this. And an interesting point about the proof. So Bangert is not typically considered to be a symplectic geometer, more a dynamicist or And this argument uses techniques he developed for working on the asymptotic plateau problem. So it's like a new thing. It's, you know, and this kind of behavior maps from C into a complex manifold is well studied in complex geometry, and they call it non-hyperbolicity. Hyperbolicity, non-hyperbolicity is a big area of study, which is why my talk is symplectic non-hyperbolicity. The goal is to understand things of this type. Bangert's argument is very ad hoc. It only works for the torus. And if you're going to try to use it to generalize results like this, you really want a pure symplectic topological understanding of it. I mean, make it as topological as possible. So that's the use of Ahlfors currents. But let me get into some geometric points about these maps. Are there any questions so far?
Or what would the image of this map look like? I mean, in that example, you wrote the image is dense or something.
Yeah.
Is there anything you can say in general? Or
So if you look at complex tori, it already actually in complex tori, it's already a little interesting. It's the closure is what do I want to say? No, I mean, it doesn't have to be dense. It doesn't have to be dense. So there's an interesting example. This paper by Bangert is building on a paper by Moser. And in it, Moser has some conjectures about how these maps behave. And one of them is about if it's not a torus, does it have to be dense? And it's already false in the complex setting. So it's like it's not. But if you assume that this map has bounded derivative, then the closure is either a torus, maybe not two-dimensional but three-dimensional, or it's dense. So it's like there's geometrically, it's like if you assume that this is bounded, it behaves completely differently. And if you have one where the derivative isn't bounded, a rescaling procedure can produce one that is bounded. So the existence of such a map with bounded derivative versus unbounded derivative are equivalent. It's like if you're studying the geometry, it's maybe nicer to just assume it's bounded, and then you can say things.
So the image is always a kind of cylinder that the compact factor and the non-compact factor have arbitrary dimension, right?
What do you mean the compact factor and non-compact factor?
Well, it's always a torus times the Euclidean space, but you can have any distribution of the dimension between the two factors.
I mean, it's
Take, say,
it can be like periodic in one direction.
right, CK mapping to T to the whatever dimension. There is no reason if it's periodic in one direction that it should be periodic in the other one.
That's right. It can be periodic in one, but not the other. And these are in general not proper curves.
Right.
And so just a geometric point about the complex plane is if you take disks of radius r, then the length of the boundary divided by the area that goes to 0 as r goes to infinity. Just one grows like a line and the other grows like a square, right? So, but this isn't true in the hyperbolic plane, right? This tends to 1, right? So it turns out that this is a conformally invariant property of the plane. It's called the Ahlfors lemma. If you have a conformal factor, maybe with isolated zeros, there exists a sequence of disks and this is with respect to the conformal metric.
So lambda, what regularity does it have?
I mean, it should be continuous, but if so, this reference I checked, and it's not clear to find this exact statement in the reference, but the idea is in it. I think a very nice proof of it is in Gromov's work. This book on metric structures in Riemannian and non-Riemannian varieties has a one-page proof of this. It's just a thing in pure conformal geometry. But the idea is if you map a complex line into a Hermitian manifold and you take the pullback metric, it'll give you such a conformal factor. So this tells you about the lengths and areas of subdisks of your complex line in an ambient manifold. So use the pullback metric. That's why you allow isolated zeros for singular points.
Or still a question. This isn't true for any sequence of increasing disks.
No, but it's true for a typical sequence of increasing disks.
Oh, what is it?
It's like if you look at the measure of so the way this is proved is using that some integral diverges. So it's like if you had some kind of positive area part of the line where these disks disobeyed the inequality, it would contradict the proof. So it's like kind of, if you take a typical sequence, it should work, but it's difficult to phrase it formally. And these disks are actually disks, like they're metric disks for the Euclidean metric.
Oh, okay. I misunderstood.
Oh, sorry.
Yeah. Okay. They're just whatever distance R type things.
Yeah.
They're not.
Okay, so this motivates the main definition of the talk. So you call a current, which is a linear map on two forms, an Ahlfors current. If there exists sequence of holomorphic disks such that when normalized, they tend to T. And
What is X?
they satisfy star. It's an almost Hermitian manifold. So kind of throughout the talk, there will be a Hermitian structure in the background or an almost Hermitian structure. But like this estimate, if you set aside this estimate for some Hermitian structure, you set aside for all of them, because it's a compact manifold. So it's like the Hermitian structure is not terribly important. It's mostly a complex structure thing.
So these things are boundaryless then?
Exactly. Yeah. Yeah. So that's the exciting part. So if you have a complex line, then by Ahlfors lemma, you get a it's the same story. You get a sequence of disks satisfying this, and then by Bonnecke log, you can take a subsequence which converts to an Ahlfors current. So if you have a complex line, you get an Ahlfors current. But the joy of an Ahlfors current is that it's a homological object. It has a homology class because it's closed, exactly because the length of the limiting thing tends to 0. So unlike complex lines, you can take its intersection numbers, you can pair it with forms. It has, kind of a rich topological life. So just a couple of points about this definition. It appears, it seems, first in work of Duval from 2008, where he attributes it to McQuillan. But then McQuillan has a later paper where he says this attribution is not 100% correct, and it's actually due to Duval. So it's due to some combination of Duval and McQuillan.
But all forces there. In the end anyways.
Yeah. And just let me give 2 examples. Oh, I'm sorry. The basic ones are just rational and elliptic curves. So a rational curve, you just take disks, missing some small set. And then for the elliptic curve, you just take large disks and its universal cover.
Okay, so about the sort of origin of this. So there's an old paper by Sullivan about cycles for the dynamical study.
Yes.
So you know that probably.
Mhm.
So this is exactly the idea from that paper and what in foliation theory is called the Well-Sullivan cycle. So a leaf of non-exponential growth always defines a cycle in this way. And here you're using the Ahlfors lemma to say that, the growth at infinity is small enough that you get an asymptotic cycle.
Mm-hmm. Yeah, that's and these are in fact examples of complex cycles.
Right.
In his work, yes. Yeah, in this paper of Sullivan, he has the torus as an example, right? Because beyond taking complex lines, you get other complex cycles by taking just algebraic subvarieties, and then they have sub-exponential growth. So there's like a whole much richer class beyond the Ahlfors currents. But the Ahlfors currents have a certain nice properties, or yeah. Okay, so every complex line gives you an Ahlfors current, and in fact, the converse is true. It's a theorem by Duval in 2008. It's like a 10-page paper. So in particular, we get this chain of equivalences that there exists a complex line is equivalent to there exists an Ahlfors current. And this is equivalent just by unraveling the definition to the existence of disks satisfying arbitrarily strong linear reverse isoparametric inequalities. So it's like a geometric. So the idea is studying symplectic non-hyperbolicity. You want to get some kind of topological understanding of these lines. It's very difficult to work directly with the lines, but you can instead work with Ahlfors currents. And then you just need to understand holomorphic disks and some geometric inequality about them. I mean, this is a very nice inequality. It doesn't talk about derivatives or anything. It's reparameterization invariant. It's just a geometric inequality. And
How do you go from an Ahlfors current to a line? Do you I mean, the most obvious thing to try maybe is to take this sequence of growing disks and pass to a Gromov limit, or like a subsequential Gromov limit. Is that how it works?
that's how it works, yeah. And actually, Duval's result is stronger than this. He doesn't just say that there exists a J-holomorphic map, but if you take a if you take a compact set with positive measure for the, measure induced by the current, then there is a complex line passing through it. So he localizes the line. This is
I think I'm missing something, because if you just take a subsequential limit of these disks, you could have bubbling if you try to pass to a Gromov limit, right? So how do you roll that out?
I mean, bubbling would also be nice, right? Because that's a
Oh, I see.
okay, fine. But no, I mean, it is a 10-page paper. Something needs to be done. So it's like beyond bubbling, there's some question about like bubbling at an annulus and things like this. I mean, it's essentially like a covering argument, but the algorithm constructed is somewhat involved. Okay. And then the key takeaway of the talk, the thesis of the talk is Ahlfors currents are like rational curves. So I'll define this in a couple of ways, but just let me say, you think kind of maybe it's a nothing analogy because disks are like rational curves, complex lines are like rational curves, but I think the analogy is surprisingly strong. So the first point in the analogy is the way you construct them. So you say, constructing a complex line is some kind of weird process. It's not like the standard continuity method, but Ahlfors currents, it's disks, which can be constructed with continuity method, and then some inequality, which you try to get. So by thinking instead with Ahlfors currents, you can construct them and therefore lines with continuity method. So you take a closed symplectic manifold. And it admits a metric of non-positive curvature. Before I state the conclusion, I just want to point out, retracting onto a Lagrangian is not the same as deformation retracting onto a Lagrangian, which would be impossible. So for instance, this torus retracts onto this Lagrangian. It's like very easy to retract onto a Lagrangian. This is a coordinate fiber, you just take the projection. So this maybe looks strong, but it's not as strong as it looks because it's not a deformation retraction. And then the second assumption is some weird geometric thing, but I just stated it that way for convenience. It can be replaced with a topological assumption that omega is aspherical and the fundamental group of X has a homological Dane function of at most quadratic growth, which is just a topological assumption. Okay, so then the conclusion is if you multiply X by a torus, then it has this J homomorphic torus, and as you deform J within the tame J's, the torus deforms as an Ahlfors current, and then you can extract a complex line from it. So again, this is like kind of a proof of concept. This is just the simplest case where you can use this technique. But I expect you should be able to use it more generally. And in fact, there are cases where you can. Okay.
Can you control anything about the direction of this map?
Yeah.
Like, I guess if you take that map and project it onto T2, could you give it a direction in that way? Or
So yes, so let me say these Ahlfors currents, like it's a sequence of disks satisfying this reverse asymmetric inequality.
It has a homology.
Yeah. So there are these forms called hyperbolic, and it's you take some two forms, say, and you lift it to the universal cover, and if it equals D of something bounded, it's called hyperbolic. And then it just follows from this definition of Ahlfors currents that hyperbolic forms vanish when paired with Ahlfors currents.
Yeah.
Yeah. Exactly, by Stokes theorem. So if you take, and the fact that disks lift to universal covers. Yeah. So if you take, say, a torus times genus 2 surface, then the Ahlfors current will always be in the torus homology class. Because the fundamental form of the genus 2 surface is hyperbolic. So these can be controlled with.
Sorry, but can you give it a mixed class? So it's not strictly the second factor, it's sort of mixed but projects surjectively to the torus?
I think it's a mixed class, then the fundamental form of the genus 2 factor has to pair with it positively. So then that should be forbidden by the homological condition.
So you can't use the 1-1 classes. Do this.
I don't believe so.
Okay.
Or, yeah, I guess my follow-up is that, where can you control the homology class of the, well, you know, the homology class is in the two torus, can you control the direction of that homology class? Or, oh, no, it's a two-dimensional class. Right?
Yeah.
Yeah.
Okay. I mean, you could ask if you multiply by some n torus or something. You know, can you control it within there?
Yeah, perhaps that's what I was thinking.
It's so the method, I don't control it in the paper by the construction,
Yeah.
but with I think stronger geometric assumptions than I make, you can control the homology class. This is because I constructed it as a sequence of
Okay.
Okay, sorry. Oh, just let me give an example. If you take a symplectic manifold, which is a product of surfaces, with the product symplectic form, then if all genera are greater than or equal to 2, then no came to J as a complex line. This uses hyperbolic forms like I just mentioned. And then if not, then every tame J contains a complex line. So this answers a question by Ivashkovich and Rose. Okay. I just want to make some remarks about this proof because I think the proof is, it's like the technique is the point.
So the note J as a complex line is maybe the simpler part, and then the every tame J is your theorem.
Yeah, so if one of the factors is a rational curve, then it's Gromov, just 1985. And then the new case is when there are no rational curves, but there's still a torus.
Okay.
And this actually the case when they're all tori recovers Bangert's result. So it generalizes.
Gotcha. Yeah, sorry, I'll let you get to the point.
No, I love when people are. It's always depressing after a talk when no questions have been asked. Okay, so I'll give the case for the torus, and just if you draw a picture, think of the board as being the universal cover of the torus. And you take this Lagrangian, some kind of Lagrangian cylinder. Then just using standard techniques, you can construct J holomorphic disk for any J. And then you want to control its boundary length compared to its area. So this was studied by Gromon and Solomon. And then later by Duval, who shows that you can get such estimates just by using a monotonicity formula. The monotonicity formula gives you a reverse isometric inequality of this form, but C depends on the length scale at which the monotonicity holds. So I really need to control the constant. That's the key point. So I want some monotonicity formula that works at very large scales. So what you would think is I get some constant for this cylinder, and then this has the scaling symmetry, so I can scale the cylinder and I get a bigger length scale. So you can hope you get a better inequality. But if you look at the arguments of Gromon and Solomon and Duval, they use C1 bounds on J, which is destroyed by scaling. So the key point is this like kind of C0 robust monotonicity. Then once it's C0 robust, then the scaling argument works. And then for other cases, it's similar. It's this doesn't really need to use scaling. It's like kind of easy to estimate this for given Lagrangian. Okay, any questions about this? So the idea is if you have some kind of sequence of Lagrangians in the universal cover that get bigger and bigger, then it just, you should get very strong reverse isometric inequalities, and then you just use standard arguments to construct disks on them. So it splits constructing a line into a standard argument of constructing disks and then estimating them using monotonicity, which is again like a standard argument, but you need some kind of robust form of it.
I had a silly question about this maybe. So the way I understand the standard monotonicity formula is you have two functions. You have you have two functions of R. You have, the area of the boundary and you have the area of the disk inside it.
Mm-hmm.
And you take the derivative of the area of the disk inside it, bound it by the length of the boundary.
Yeah.
Some function of that, right?
Mm-hmm.
And so I'm wondering where on that you need to restrict the length scale that you're working at. Because I guess
So
I mean you're in some in like a closed manifold. I guess this argument doesn't make sense once you go outside the injectivity radius or something.
yeah, so the injectivity radius is.
Oh, but here you're on like R2N.
Yeah, but it's with Lagrangian boundary.
Oh.
So instead of emanating out from a point, you emanate out from this Lagrangian.
Oh, okay.
And then once you hit the injectivity radius of the Lagrangian, it stops working.
Oh, okay.
So it's just the normal injectivity radius of the Lagrangian is the relevant length scale.
I see.
Okay. Okay. So that's the first point in the analogy is that Ahlfors current is going to be constructed with a continuity method. The second point is bubbling. So rational curves arise as a source of flexibility, right? Because they form bubbles, and that's part of why you don't have compact moduli spaces. In complex geometry, complex lines are even a stronger source of flexibility. So if you have no complex lines whatsoever in a compact manifold, then it actually has a biholomorphism invariant metric. So all the complex geometry just reduces to metric geometry, which is very rigid. So there's this comparing pseudoholomorphic curves, you get this. You have a sequence of closed holomorphic curves. If their areas grow faster than their genera, then a subsequence after normalization converges to an Ahlfors current. So this was known, DEMI has a result that if you have such a sequence, then he doesn't say it converges to an Ahlfors current or anything, but he says you can extract a complex line by rescaling. But that's a very strong argument. It's a very nice argument, but it doesn't tell you anything about that complex line really. But this tells you that their homology classes limit to the homology class of an Ahlfors current. So you're able to get some aspects of this rigidity even when you have complex lines, because you can control the homology classes of the Ahlfors currents.
So does this ever happen? Limit as genus over area goes to 0?
Yeah, like
yeah, I guess I was thinking of like, I mean, if you look at like the Fredholm index form for closed holomorphic curves, right? Then at least, or in dimension 4 at least, or even higher dimension, then there's a term, there's like a term that's linear in the Euler characteristic, and there's a term that's linear in, the Chern number. Oh, okay.
This happens, for instance, in projective spaces.
Oh, wait, or it doesn't happen in CP2, right? Because I guess in that case,
Well, like for instance,
at junction, you get that the genus is about the square of the area.
there's no assumptions about like embeddedness or anything. They're just maps. So you should, like, you can have like a genus 2 curve and
okay.
big.
I guess I'm thinking of a very specific situation, which is embedded curves and format.
I see.
It doesn't
Okay.
really happen there. Yeah, but in other cases, okay.
Yeah. So unlike the classic Demai's argument, which is a local rescaling, this requires global information. And the idea here is that the genus of a holomorphic curve is approximately equal to its hyperbolic area. So then if the area as a sub-object blows up, that means that the induced metric has some big conformal factor, which you think is tamping the curvature down to 0. And this happens on average. So you think if you take a typical disk in the universal cover, then it should have small curvature on average. But to say that requires some result. And the result is that the geodesic flow on a hyperbolic surface is mixing. It's like this intermediate step. It's just like a pure dynamics thing. It's from a paper by, I think it's kind of known, but the proof I found is in a paper by McMullen and Eskin. So it's just a nice simple point. This takes just the front and back of a piece of paper to prove, but it's nice. And it says, for instance, if these curves don't tend to a homology class which is populated by an Ahlfors current, then their genus bounds their area from above, which is the reverse of the Castel-Nuovo bound, which people care about for the scope of Kumar-Balfa conjecture. So it's like you can use homology to get these interesting geometric bounds. Any questions about this? Okay. And then the last prong in this analogy that I want to talk about, moduli spaces. So when I was talking about this, when I was working on it, I would talk to people, and universally they said, what about the moduli space? Because people care so much about the moduli spaces of rational curves. And here you can't expect the same kind of behavior, because pseudomorphic curves are solutions to an elliptic PDE. They lie in finite dimensional spaces, whereas these are currents. They lie in an infinite dimensional linear space. It's just a completely different kind of object. So instead of expecting some kind of finite dimensionality, you might expect some kind of linear well-behavedness. And this is the result. It forms a compact convex set.
So if you take like whatever T4, you take these, I guess, T2 or planes that point in irrational directions. Do they? I guess you can. Well, you have some kind of foliation, right? By planes. Do they all give you the same Ahlfors current?
I think they do. Yeah.
Oh, okay. Yeah. So then in this case, that would be the space would be a point or something.
Yeah.
Or I guess. Or yeah, I guess what's the space of Ahlfors currents for T4, the standard complex structure?
It should be, if you think of the second homology in T4 as being T4 before you take the quotient, it's just the things represented by lines.
Okay.
It's like the Grassmannian.
So, and so each of these would be represented by one of these linear foliations.
Yeah. So both of these are actually new in the classic setting of complex geometry. This one, it's proved using the flexibility of disks. So you think a disk, before you assign its boundary conditions, has an infinite dimensional moduli. So it's very easy to perturb them and glue them and things like this, which is one of the strengths of working with Ahlfors currents. Yeah, so just to summarize, I think this theorem by Bangert is amazing. I mean, it says that there's something new to study, and it's connected to complex geometry. I mean, there's a lot of things in complex geometry that connect with these kind of objects. And Ahlfors currents, I think, open up the study to symplectic and topological methods. And I think these methods, it's interesting in that, first of all, it's like Bangert's result uses the asymptotic plateau problem. This one uses something akin. This uses mixing of geodesic flows. This uses flexibility of disks. It invites the use of new techniques that aren't restricted just to the problem. Because using Ahlfors currents, you're just talking about disks, which are such a central object of study. So I think it provides like a pure geometric motivation for more quantitative study of pseudoholomorphic curves. I think it's not unreasonable to expect interesting applications to things like differential geometry and of almost complex structures or symplectic geometry or dynamics or things like this. So thank you very much for letting me come tell you about this.
Questions?
Not many people have studied this Bangert paper. Right? Why is that?
I don't know. So like Viterbo had a student who studied it and she used Floer theory. I think it's kind of, the thing about Bangert's paper is it's not very, the argument doesn't have any places where it easily generalizes to other cases. It's even like, you think the key point of the argument is used is that the universal cover of T4 is the standard symplectic Rn, but then so is the universal cover of a genus 2 surface. And the argument doesn't work there. So there's some kind of like weird geometric estimate that doesn't transfer. So it's not easy to read the paper and see how you should proceed. And these using Ahlfors currents Ahlfors currents are defined 10 years after Bangert's paper. So I think it's maybe something like Bangert had this paper, and then around that time, there's writings by Gromov and Sikharov and other people kind of
So
excited.
Bangert was answering a question by Moser.
Yeah.
Moser,
And I think around the time there was a lot of excitement, but it wasn't clear how to proceed with the study and it kind of died out. But then in the intervening period, this new kind of complex geometric techniques have arisen that I think make it feasible to study.
So you said something about intersection theory. So can you, can you intersect two Ahlfors currents together, or is it more?
You can. It's like the thing is there are limits of disks. So it's like it's not so easy because you have to like commute with some limit, but I think it's more common to intersect them with kind of static sub-objects. The idea being if you're in a four manifold and you have some curve, you think of it as a divisor. And then the intersection number of an Ahlfors current in the divisor is something like the asymptotic intersection number of the holomorphic line and this divisor, which is like the asymptotic number of zeros of some analytic function. So I think that's more commonly studied. But actually, like Ahlfors currents are
you have to show this thing is independent of the sequence of disks you choose.
actually that's a point maybe I didn't talk about. Given complex line, you can take many homologically different Ahlfors currents out of it sometimes. So there's not a one-to-one correspondence.
Okay.
Yeah, but Ahlfors currents are complex cycles, and I have a paper where I show that complex cycles and holomorphic curves have positive intersection number. So it's like something can be done, but you need to be careful just because they're currents. It's like easier in this case because they're geometrically defined. So in complex geometry, Duval, the same Duval has been mentioned 8 times in this talk, has a result that they're laminar currents in the sense of Liubich and Smiley and Bedford. And you think if you have this laminar current and then it has, for some homological reason, zero intersection with another laminar current, they might be leaves of the same foliation. And you might be able to use these kind of things to construct a foliation, which would make progress towards generalizing this theorem. So I don't think that's unreasonable, but it seems difficult.
Is there a compactness statement, or like does it make sense to ask for a compactness statement?
For Ahlfors currents?
Yeah.
Yeah, sorry, this is already part of it. It's just this was known.
I mean, do you know what the
It's-
compact?
They're in a Banach space, so they're weakly compact. It's just Banach log loop. They have bounded mass.
But there's some content to that, right? Like you have to show that a weak start limit of Ahlfors currents is again an Ahlfors current, or is that easy to do?
Yeah, it's you just take a diagonal sequence.
Oh, okay.
Yeah. Yeah, and then there's like a similar kind of not really compactness for complex lines, because if you can't extract a limit, it means that some derivative is blowing up, and then you can rescale, and then bubbles are also complex lines. So it's like complex lines are strange in that they have kind of automatic compactness properties, but you can't deform them easily. So it's like they have like kind of the opposite problem that you get from closed holomorphic curves.
Okay, if we're all set with questions, let's thank Spencer again.